Okay, so in today's class, we will discuss von Neumann double Comitant theorem. Okay, and this is a more general theorem for algebra containing in B of H, where B of H is the bounded operators on Hilbert space. And we are only going to prove it for finite dimensional algebras. And we will later prove it for a general algebra containing, general C-star algebra, general algebra containing in B of H. Okay. So we need some definitions for that. Suppose, so we are going to deal with algebras containing in matrix algebras. So let's take just a set S contained in M and C or some a set, any set. Okay. Then we denote S commutant, S prime, S commutant equal to all those matrices or operators, all those A in M and C, which commutes with such that AS equal to SA for all S in S. Okay. It's just the commutant. It's like, this theory is very similar to what we do. Here there is no orthogonality, but later when we discuss Fock spaces, we will see that this commutant is there is some relation between orthogonality and commutant, and something we will see later when we discuss Fock space. Okay, so this is all operators with commutes with this S. So if S is equal to S star, that is if maybe I will use small a, all a. So if if A is in S, this implies A star is also in S. If S is closed under adjoints, then S prime is a unital. It contains identity, of course. It's always contained identity. Unital star algebra. It's of course an algebra. If something commutes with some element, then it's scalar multiple also, scalar multiple of that operator also commutes with that. And if A, B commutes with some S, A plus B also commutes with that. And so it's an algebra. So S prime is an algebra. On the other hand, if A commutes with S, then A star commutes with S star. So if S is A commutes with all of S, then A will commute with all of S star, so which is equal to S. So because of that, it's a star algebra, unital star algebra. Unital means it contains identity, and star algebra means it's closed under star. Okay. So if S is an algebra, we don't have to worry about all these things. So that is our part. So S prime is a unital star algebra. So in particular, if you take S double prime, which is equal to S prime of S prime, okay, this is a unital star algebra. This contains identity. Unital star algebra. Of course, if S is equal to S star. That condition, we are assuming that condition. If S is closed under adjoint, then this is true. S is just a set. So in particular, star algebra generated by smallest star algebra containing S, which is just you take the star, you take all sorts of products, you take all sorts of sum and other things, and you can form an algebra. And that is algebra generated by S. This is contained in S double commutant. Okay. This is very similar to if you have orthogonal complement, then the M is contained in M double perth. Okay, it's something similar to that. The question is whether it is equal to that. Okay, that is the question. So that is what the theorem. The theorem is the following. A is contained in M and C, a star algebra, unital star algebra.
Sorry, what the star algebra bracket is?
Star algebra generated by that. That's what I meant. Algebra generated by that.
Okay.
Okay. Star algebra generated by S. Usually we write algebra generated by S or something. Or vectors. In the vector space case, span of that. Here you have to take all span, all linear product, all star, everything combined. It's a polynomial in S and S star kind of thing. So that will all polynomials in S and S star with complex coefficient, that will give the star algebra generated by that. And that is contained in S double prime. Okay, that is for a set. But if you have an algebra A contained in M and C, which is a unital star algebra, then this is the double commutant theorem. A equal to A double commutant. So this is the theorem. In particular, as a consequence, that's what I mean. In particular, if S is contained in M and C, any set, such that S equal to S star, okay, then the star algebra generated by then it's an algebra is enough, because S is a star, so it's star algebra also. Algebra generated by S is equal to S double comitant. So that is the smallest algebra containing S. Smallest star algebra containing S is S double comitant. So that is the theorem. Okay. S is equal to S double comitant. Okay. So how to prove it? So this is what we want to prove. So, I mean, here there is no topology involved. So in infinite dimension, when it is in B of H, A is equal to A double comitant if and only if it's closed in some topology. Okay. So which is so beautiful, this statement is because A equal to A double comitant is a purely an algebraic statement, something commutes or something. It is closed in some topology is a purely topological statement, which a priori there is no connection between them. But when they are operator algebras, there is a connection between them. So that is why this theorem is very beautiful in the infinite dimensional context. Okay. So proof. So we know that if you have a, so clearly A is contained in A double comitant because A is an algebra. A commutes, I mean, A comitant is all operators commutes with A. A double comitant is something commutes with A comitant because A comitant commutes with A. So A is contained in A double comitant. So this is okay. This is okay. We only have to prove the other way. Okay. So now to prove A double comitant is contained in A, let X be in A double comitant. Something which commutes, something in the double comitant which commutes with the comitant of A. Okay. Okay. So first we will do something. We will notice something. After that, we will apply to a slightly more general case. We will apply the same thing, and then we'll get the theorem. Okay. So the idea is you take a xi, which is an element in Cn. Okay, that is our underlined Hilbert space where MNC all operators are acting. This is an operators acting on something. That is our Cn. So you take Cn. Then you consider this A xi. A xi is all operators. A xi. You fix xi and vary this A. Okay. So this is I form a set like this. Then this set is, this is a subspace. See, right? This is a subspace. Scalar multiple of that. Because A is an algebra, I multiply by scalar or take the sum, it's an algebra. A1 xi plus A2 xi is A1 plus A2 xi, so it's an algebra. It's a subspace of Cn. Okay. So now you take the projection. So you call this as K or something. K. K is equal to K. I call that as K. Now P be the projection from Cn to K. Orthogonal projection. Okay. We will define this projection for a general Hilbert space most probably in the next 2 classes in the graduate analysis. So, but I am assuming you know these things from linear algebra. Okay, this is an orthogonal projection. We have already discussed projection then. So P is an orthogonal projection. Okay. Onto K. Now the claim is the following. P is in A commutator. That is a question. P commutes with everything in A. Okay, that is the claim. So for that, what do you have to do? So let something in K. So anything in K is of this form, Azi, right? Azi. Okay. So P commutes with Azi we want to. A is this and B is in A. Okay. Then P B Azi equal to, of course, P B Azi, right? I'm taking Azi, which is a vector in K. B is a matrix or operator. B is in A. Okay, then PBASI is PBASI, of course, PBASI, where you can put PB. BA is also something in this. But then P is a projection onto K, so it acts as identity on K. So this is just equal to BASI, right? Clear? ASI is a vector. Xi is a fixed vector, a fixed vector. And ASI is an element in K. So that is why we have defined K to be like that. Okay. Now, if you have a B acting on ASI, it's just BASI, right? That's all. But P acting on ASI, BASI, AB is a BA is also in A. Okay. So that is in K. This element is in K. So P acting on that is identity. Okay. On the other hand, BPASI equal to, but then BPASI, okay, but PASI is ASI, so which is again PASI. Okay, this implies PB equal to BP on K, right? Clear? This is direct verification. Okay? BP equal to K. So now, I mean, you want to check something, some two operators are same. Okay, we want to check that PB equal to BP. Okay, that's what we want to check. To check that, it is enough to check on K and K per, right? Something on K and its orthogonal complement. It's enough to check. So now let eta be some vector in K per. That is, eta is in the orthogonal complement. Eta, the inner product of eta with any vector in K is 0. That's what it means. Now let us act PB eta. Okay, PB eta. So we want to say that PB, what is PB eta? No, let first BP eta. BP eta. P eta is 0, right? Because P is capital P is orthogonal projection onto K. So eta is in the K per. So P eta is 0. So this is equal to 0. Okay. Now we have to say that PB eta is also 0. That's what we have to say. Now we compute PB eta. We cannot directly compute. So we take the inner product with any ASI. Okay. But then P is in projection, which is self-adjoint. You can take it to the other side. Okay. So I take it to the other side. I take the B also to the other side as a star. Okay. A psi B star PA, right? Correct. Now PASI is ASI. Okay, because ASI is in K. Okay, so this is equal to eta B star. PASI is ASI, right? And this is anyway in K. Okay, this is in K. So that's why P acting on its identity. So it becomes ASI. And this becomes B star ASI. But that is also in K. But eta is in the orthogonal complement of K. So this is equal to 0. Okay, since eta is in K per. Okay. So we have proved that BP eta is equal to 0. So this is true for all A. This is true for all A. Okay. So this implies PB equal to BP on K perp also. So PB coincides on K and K perp. So both these things implies PB equal to BP on CN. Okay. I mean, I'm writing each and everything, every word. Okay, that's all. So this implies, this is what it means by P is in A comma. Okay, any doubt? Shall I go through the argument? Anything? I'm just taking you take a single xi, act the whole algebra on xi, you get a subspace. P is a projection onto the subspace. I have shown that P is in A comma. That's all I have shown. Okay. Now if I take a x, I have taken a have I taken? X is in A double commuton. Now I have taken X is in double commuton. Now X is in A double commuton. That means that is X commutes with everything in A commuton. Okay, that means XP equal to PX. Okay, what does it mean? If it is in double commuton, what does it mean? So XP xi equal to PX xi. Okay. XP, wait a minute. No, X xi, sorry. Now X xi, X acting on xi equal to XP xi, right? Because xi is in K. Okay, P acting on xi is xi. Okay, so XP xi, that is equal to PX xi, because that commutes with it, no? So that is equal to PX xi. X xi is some vector, we don't care. But P, when it acts on P, it brings it to K. So it has to be of the form some A times xi. So this is equal to some A naught times xi. Wait a minute, for some A naught in A. I'm saying xi, you take xi, that vector xi. That I can write it at X times Pzi. But since X commutes with P, you can take the P outside. So that implies this is equal to Pxi. Xi is some vector in Cn. P acting on that will bring it to K. but K is just capital script A xi. So it has to be of this form. Okay. So xi equal to, so xi is equal to A naught xi for some A naught in A. If we take any vectors, we started with an arbitrary vector xi. Then we got corresponding to that vector. We want to show that x is equal to some A naught, right? But on a particular vector, x is xi equal to A naught xi. But this is not enough. This is just for a single vector. For a different vector, then we may not get a different A naught, right? So this is not, we want to prove basically this. X is equal to A naught for some A naught in script A, the algebra A. Okay. But we have proved that if you take a vector xi, on that vector, x is equal to A naught xi for some A naught. Okay. But if we prove this for a linearly independent vectors, a single A naught for all linearly independent vectors or for the basis, that is enough. I am just saying, so this says that if you take an x in A double comitant, then there exists a naught such that xi equal to A naught xi. This is for a x and a xi. Okay.
So xi here is restricted to K, right?
Xi
Is in K.
Xi is in K. Yeah.
Okay, but then if xi agree, I mean if x and A not agree,
On
I mean,
xi.
you will
X and A agree on xi. That's all I'm saying.
so we will prove that x agrees with A not on all xi in K.
No, we will prove it for not all xi. That we don't want. We want to prove it for whole Cn.
Okay.
For that, for a xi, there exists a naught such that xi equal to A naught xi. I want to prove that xi equal to A naught x so this is let xi1 up to xn, okay, is a basis, possibly orthonormal basis or something, basis for Cn. Okay. If we prove there exists some A or something, maybe A naught, maybe A naught prime, whatever, A naught in A, such that x xi I equal to A naught xi I for all I. Okay. Then we know that x equal to A naught because it agrees on a linearly independent vectors. I mean, it agrees on a basis. So it has to be same. They are linear operators. So it has to be same. Okay. That's what we want to prove if we want to prove. But we have proved for one vector, but we want to prove it for some linearly independent vector.
In that case, x will be equal to A naught.
Correct. That's what we want to prove, right? We have chosen x in A double prime. We want to prove that x is in A. So we have to get an element in A, which is x equal to A, right? So the whatever that A naught. Okay. So that's what we want to do. So for that, we do the following. So what do we do? We take the tensor product, but maybe tensor product may be confusing. So let's take the direct sum. It's okay. Tensor product. If you take, see, if you sum something n times, that is taking is the product. N times some product is sum it n times, right? So that's what we are going to do. We take the direct sum instead of tensor product. Tensor product, if it is confusing, you can take the tensor product also if you are familiar with that. Otherwise, we will take the direct sums. Okay. So let me define pi, a map from, we can take it from MNC itself, MNC to MNC. I write tensor, but you don't have to worry about it. MNC, which I am saying is equal to this. MNC, direct sum, MNC. I can identify with this. You can forget this, okay, if you want. But these two are same. I define tensor product, if you think about it, these two are same. Maybe this will be useful for the assignment I gave you, this identification. Okay, you can think about it. Okay, so I can take it. This is n times. I'm taking direct sum, which we are all familiar. Okay, n times this. So this direct sum, this thing sits inside. This is an algebra acting on Cn, right? MNC is a matrices, is an operators on Cn. MNC direct sum of two matrices means it's acting on, this is matrix on Cn direct sum, is a vector spaces, direct sum Cn, right? Each one will act on the corresponding. Okay. So how do we define pi? Pi of A equal to just A direct sum A, which is nothing but this diagonal element. I mean, you have Cn direction, Cn. Okay. So, I mean, what is Cn to start with? It is C direction, C. Which any operator on that, it's a matrix on that. So what is Cn direction, Cn direction, Cn? What is an operator on that? That will be a matrix containing elements of MNC, right? Right? I mean, I'm just saying M, we want to talk about the operators on this, or maybe I will use the notation used in the graduate analysis class, which is just B of Cn direct sum Cn, which is just operators on this, okay, which is also matrix, but I write it like this, which is just Mn, okay, acting with entries coming from MNC. Is this clear? Right? If you have some matrix like this, A1, these are all entries coming from A11 up to A1 n, A21 up to A2n. These are all matrices like this, AN1 up to ANN. These are all where Aij is matrix in MNC. Okay. Now this will act on Cn, any element like this, right? If you want, maybe Xi1 up to Xin, where this Xi are in Cn. Okay. Which you want, what is that? This is just going to be summation A I K Xi K AIK. So, right? It will be like this. A1K, A summation A2K up to summation ANK Xk. This is a vector. This is again a vector in, you will get a vector in Cn and you will get a vector, n such vectors. So, okay. You can take the direct sum of Hilbert spaces, then you can take whatever the same Hilbert space, then you just take the matrices of operators on that. Okay. Matrices have usually entries from scalars. Instead, I am taking operators as entries. Okay. This is fine with everyone. Is okay. Okay. Just so that is what this pi is. Now I am saying pi is nothing but a direction. So pi of a in this notation, pi of a is nothing but a like this, zeros everywhere. Diagonal a. That's what I'm saying. Pi of a. Okay. So this is in MNC. The a is in MNC. A is in MNC. And this is in Mn of MNC. Okay. Diagonal. Okay. Whatever. But there's an operator on Cn direction Cn n times. Okay. That's what this is. Okay. Okay. Why I am doing this? So now I have this pi a acting on that. So I have taken a vector Xi1 up to Xn, which is a basis for Cn. Okay. Each Xi is a vector in Cn. So Xi1 direction Xi1 up to Xn is a vector. Let me call it Xi tilde. Xi tilde is a vector Xi1, Xi2. These are all linearly independent vectors in Cn, but I am taking a single vector like this, which is in Cn direction up to Cn, right? N times Cn. This is a vector Xi1, Xi2 up to Xn. Okay, this is a vector. Now I take this pi of a Xi tilde. Okay, I call this as k tilde. Okay. Okay. Now, for the time being, let us see what is pi of a commutant and double commutant. What is pi of a commutant? Claim. Let me claim and then explain this. Claim. Pi of a commutant is equal to precisely, I mean, you know that pi of a, all these things are, if the commutant is taken in that operators on Cn direction Cn, right? That is where the commutant is taken. Okay. So that they are all matrices with entries coming from MNC. Okay. But A commutant is in MNC. I'm saying this is precisely equal to entries where the entries are coming from A commutant. Okay. Pi of A commutant. Pi of A is just A diagonal. Okay. You just do the computation. We'll do the computation. I will see that pi of A commutant is M1 with the entries coming from A commutant. What does it mean? Pi of A is what? So if you have some vector, X is in Mn, MNC. Okay, which is, by this I mean matrices with entries in MNC. N cross N matrix with entries in MNC, which is N square plus N square matrix, right? n square cross n cross n, we will have n square matrices, right? So that is what X is in MNC with entries coming from MNC. So now if we, so which is equal to Xij or something, which is equal to some Xij, okay, where Xij is in MNC. Okay. Now what does it mean? X times pi of A equal to, just compute pi of A X. Okay. So which is just means Xik. Okay. For I mean the each entry Xi, I mean the product ijth entry of this product here, ijth entry of this product should coincide. That's what it means. They compute. So Xik A what pi of A Kj is equal to pi of A Ik summation X Kj, right? That's what it means. They commute means that's what it means. But then pi of A is a diagonal matrix.
Commute is in our hypothesis, we are assuming X is such a.
Wait. You're right. Yeah. X is in this and X is in pi of A commutator. Correct. X is in sorry, yeah, this is what I want to say. So maybe I write it like 1 second. Yeah, you are right. I didn't write the right assumption. X is in pi of A commuton, which is contained in Mn of MNC. Okay, this is what I want to say. That's the representation. So Xij pi of A Kj matrix entry of this product here. So pi, this is in pi of A commuton means X commutes with pi of A for all A, right? For all A in A. Okay. So I'm just writing it. So what is this pi of A Kj, which is just only K equal to J? It is just, I mean, it is, otherwise it's 0, right? So this is when I is not equal to 0, both sides are 0. It should be 0.
So, sir,
Yeah.
the claim you have written pi of A commuton is Mn of A commuton.
Yeah.
So inside the, like, for the pi A, shouldn't that be the curly A?
No, what is curly A? There is no curly A. Pi A is an algebra. Pi of A, sorry, this, yeah, sure. Oh, yeah. Okay, you are right. Sorry. Sure, you are. Yeah. Precise. I wrote the A is just an operator. This is algebra. Okay, this is what it is. Pi of, yeah, correct. Pi of A, maybe I put a bracket here. There is no confusion. Pi of A is contained in that. So yeah, these kind of mistakes I tend to make many times. Yeah. Okay, yeah. You are right. Pi of A, which is an algebra, which is just the algebra sitting in the big algebra as diagonals. That's all.
Yeah.
Which is precisely 1 tens are A. Okay, if you think about it, which is precisely 1 tens are A, which we defined last time. Okay, so that commutant is Mn of A commutant. Matrices coming with entries. So I have to just say that Xik, all these things are just in. So what does it mean? Pi of A is only K equal to J, this matters. Right? K equal to J, this, and I mean, this side is, I mean, here, in this sum, only K equal to J survives. Everything else is 0. On that sum, K equal to I, which survives. And this is right now, right hand side. Okay. So this implies Xij times pi of A. Pi of A is just A, right? Times A is equal to A times X. I'm only for I it surveys, right? That's what it means. For all Ij, for all A. Okay. Now this implies Xij is in A commutant. That's what it means by it's in Xij, each Xij is in A commutant. Now you can reverse this. When you have entries coming from A commutant MNC, on the other hand, so what does this imply? This implies that pi of A commutant is contained in Mn of A commutant. That's what this says. On the other hand, this way is clear. This inclusion is clear. You just write the matrix, it will commute, right? For example, in this product, you have to check this product. This product you have to check. When Xik is everywhere, I mean, this is only K equal to J, it's going to survive only for K equal to J. There it is going to survive for that. This is, maybe I will write, these are all equivalent, no? This is equivalent to this. This is equivalent to this. This is equivalent to this. Okay. So this is equal. Okay. So this is equal. Hence, okay, this is equal. This is not contained. Whatever I have written earlier statement, they are all equal statement, right? If you have any doubt, let's discuss. Okay, I want to prove that pi of A commutant is Mn of A commutant. I mean, all matrices with entries coming from A commutant. I just written the relationship and I got it. Nothing else. Just write the matrix product and you get it. That is how it acts on that. That is how. Okay. That is how it multiplies and all that. Okay. This works for Hilbert space or anything. If you take direct sum, finite direct sum, it is just matrices coming from the operators coming from the corresponding Hilbert space. Okay. So this claim is proved. Pi of A commutant is Mn of A commutant. Okay. Let's go to the next claim if this is all right with everyone. Anyway, this should be an exercise. You should try doing it. Okay. Because once you are used to this kind of language, then this should be given as an exercise. But since we are starting with this, I'm not I'm just doing. Okay. Okay. Shall I go to the next one? Okay. So the next one is next claim. Pi of A double commutant. That's what we want to see. Okay. Which is just pi of A commutant. You know, pi is just takes anything in MNC and puts it as the diagonal entry in the bigger algebra. Okay, bigger space. Okay, I'm just saying pi of A double commutant is pi of A commutant. Okay. Now, what does it mean? So, suppose if you have a x in pi of A double commutant, okay, and you have a A, so you have a in A, maybe A prime, maybe, is it confusing? A prime in A commutant, pi of A commutant. You want to consider pi of A double commutant. A prime means pi of A commutant. But then this is equal to Mn of A commutant. We know that. Okay. So let A prime is equal to Aij prime, where Aij prime is coming from A commutant. Okay. I'm just writing that. Okay. So now I am saying that x A prime is equal to A prime x. I want to verify this. What does it mean? Okay. This is precisely equivalent to the same thing we have to write. X.
Ij prime is just notation.
Which one?
A prime.
A prime is just a notation. Because I'm taking it from A prime, I'm just putting a prime on there. This is not, this prime is not prime. This is just an operator. I put a prime on there. Okay. This just means it comes from the A prime. That's all. And small aij also. Small a is also coming from A prime. So I have written it Aij prime. Just you can, if I put Aij, then it's confusing because it comes from A or something. So now you just compute this. Aik and A prime Kj is equal to summation over K equal to other way. Aik x Kj, right? Okay. This is true for all. This is true for all Ij. That's what it means by it commutes, right? They both commute. Okay. Now what does it mean? So V5 is not equal to J. This is true for all. This is true for all AIK, right? I mean, you can. I mean, this is true for all. Not just this is true for all. I mean, okay, maybe I will put here. Here I put change it to AI. AKJ. AKJ, right? And here AIK. AIK. Sorry, AIK. I'm just writing the entries. Okay. This is true for all Ij and for all aij coming in aij prime coming in a prime, right? That's what it means. You can take any akj and you can take any ij, you can do that. Suppose if you choose aij such that I not equal to j, suppose I not equal to j, okay? Suppose fix I mean fix some ij, fix fix ij and I not equal to j, okay? And choose a aij, and you choose the matrix, choose, I mean you fix a aij and you choose a aij, and aij in aij prime in aij. This is some particular I mean some fixed aij, but it's arbitrary, okay? For this ij, for a prime, and a
But the ij is fixed,
yeah
but ai
yeah. So now maybe I put I not here, okay? I not j not and ai not j not here, okay? Then it's okay.
But I j not I not j not can vary.
No, I not j not is fixed.
I not j not is fixed, but
I not j not can vary, okay? And aij equal to 0 if ij is not equal to I not j not, okay? I'm just taking that vector. For the other vector, it is 0. So that will imply what? You can even take it to be scalar if you want. That just implies that it's only for I not j not this is true. I mean, if you just substitute it, I put a prime also, okay? It's a prime. I forgot the prime, so you would have put a prime. I mean, just to be precise, because he wants to be precise. So what does that imply? That just imply if wherever that is a aij, so it just x I j naught x I j naught a, the k naught should be equal to j naught, right? I naught k naught should be equal to I naught, right? What did I do? I mean, this is like something commutes with everything in the matrix, then that should be a scalar. I'm just using that. So if x I j naught, I'm just applying in this equation. So I this a prime is only for I naught j naught. This is true. This is non-zero. Okay. So I just want to put a I naught j naught. So k should be I naught. So x I naught, right? It should be I naught. Okay, that's okay. That should be equal to a I naught j naught times this should be k should be j naught. So j naught j. Okay. So we know that I naught is not equal to j naught. Okay. So x I naught is not equal to x j naught j. So this just implies that x I mean this just says that when I equal to j not equal to j, I naught is not equal to j. So this just implies that x does it say xij equal to 0 when I not equal to j? What about xi naught I naught? Xi naught I naught xi naught I naught times this is equal to ax j naught. This is true for all ij, right? It's true for all ij. I want to say that xij is equal to 0 if when I is not equal to j. Okay? When I equal to so when j, I mean when x I naught x j naught. No, this clearly says when xi ij I not equal to j, xj equal to 0. But I'm wondering whether it says more. It shouldn't say more. I mean, for the diagonal entries, for the diagonal entries, it shouldn't be 0. So I'm just the one except the diagonal entries, everything else is 0. Okay, that's what I want to say. Okay. So have I made any mistake? X, so this is true for all ij. So X I naught equal to A naught J naught. That there it becomes 0. You can even take A I naught J naught to be a scalar. Okay. But how does it become I naught? No, wait. I just substituted I naught J naught here, right? So no, it cannot be for any J naught. This is not for all Ij. I have taken a particular J, no. See, here this is AKJ is not, I mean, this is non-zero only for J equal to J naught and K equal to I naught. Okay, so this is for J equal to J naught only. J equal to J naught, right? Now here, what has become? Here it becomes I naught, no? Here it becomes the I naught. K J naught, K J naught. Right. So what is the right expression? You tell me. I didn't sleep. I'm getting confused.
Like we know that in the summation was for all I comma j, right?
Correct. Yeah.
So now on the left side you have akj, on the right side you have aik. So that will be 0 whenever like I is not equal to I naught and j is not equal to j naught.
So what is the right expression I should write here?
So you will get x I naught a I naught j naught.
X I naught
a I naught j naught.
X I naught here.
X I naught a I naught j naught is equal to a I naught j naught.
Okay.
X j naught j naught.
This doesn't really say anything, no? Because X, what does this say? How do I conclude that Xij is equal to 0 when I not equal to J?
No, that is already for if I is not equal to J,
then it's 0.
Yeah, there will be 0.
Right. And then this is true.
Yeah, this is not true. This is only non-zero entry.
Correct. So when I not equal to J, so
this is the only non-zero entry of that X A prime or A prime.
No, now this becomes J naught should also be equal to I naught, no? When we have this, is it not true? I want to get, let me write what I want to write. Then we see, let us, whether it is correct or not. I want to say that if I not equal to J, so whatever the expression I have written, this is true for all Ij. Okay, the claim is the following. For I not equal to J, okay, Xij equals 0. That's one thing. So when I equal to J, then Xii, Aii equal to Aii, Xii. This is what I want to get. I mean, by taking maybe X, maybe I naught or something. I mean, what I mean is, I can take any AI naught. See, this expression is true for anything. So I'm choosing a AI naught. Okay. So this is what I want to get. So there is a prime here again. Okay. This is getting messy, but you please do it as an exercise. Shall I leave this in an assignment? It's not. You do this as an assignment, okay? That's what I want to give. I mean, this is just a matrix multiplication, okay?
Is it an assignment or exercise?
Assignment. The second part. First part also you write it, which you have to just copy. The second one you just do. I'm just saying this. Pi of A commutant equal to M1 A commutant. So that is done. Okay. If you want to write it, you just do this. Okay, do this as an assignment. Okay, this is assignment. Okay. Commutant equal to pi of A double commutant. Okay, pi of A double commutant equal to M1. No, sorry. Pi of A double commutant equal to pi of A double commutant. That's all. It is just entries with that. Okay. So rest assignment. Okay, this is the exercise or assignment. Okay, that's all. Okay. So what does this say? So we have got that pi of, so what we have got is pi of A double commutant equal to pi of A double commutant. Okay. Now I have taken xi tilde as a vector, which is to be xi volt up to xi n, right? Now I can consider pi of A acting on this xi tilde, which I call it as k tilde, which I have called it as k tilde, which is contained in Cn direct sum up to Cn. Is okay? Now everything is happening in the Cn direction Cn, the amplified Cn, okay? Which is Cn tensor Cn basically. Okay. So I have taken pi of A double commutant is this, which is pi of A commutant. So suppose if we have a, so I started with x in the A double commutant, no? So let x is equal to, x is in A double commutant, then pi of x, which is in pi of A double commutant, right? Pi of A double commutant. Okay. So for which, by the earlier explanation, by earlier reasoning, which is the same thing for, we used for some algebra, which is true for any algebra, right? Earlier reasoning. Earlier, I don't know. Earlier reasoning. There exists for this pi of x, there exists a in A such that pi of x acting on xi tilde equal to pi of A xi tilde, right? Is this fine? There actually maybe A naught if you it. By earlier. Okay. I mean, if you have anything in the double commutant, there actually something in the original algebra A which coincides on a single vector. But here the single vector is n vector like that. Okay, but we have taken the algebra to be pi of A, which is the tensor sitting there. Okay. So I will just write it in the tensor language. What we have done is pi of A is nothing but one tensor A. Okay, so one tensor, that is what we have written. Whatever I have written, just to understand it in the tensorial language. Okay, which just says that pi of A is equal to one tensor A, which is sitting inside Mn tensor Mn. I have used direct sum, but you can use the tensor language also. Mn tensor Mn. Okay. What we have got is pi of A commutant is equal to A commutant. It's like this. MNC tensor A commutant. That's what we got. If you just think about it. Okay. So, and pi of A double, I mean, the commutant is outside. Pi of A double commutant is nothing but one tensor A double commutant, which is what we got it finally. Okay. So, our new algebra is one tensor A, and our double commutant is one tensor double A double commutant. So, for any element in the double commutant, there is something in the original commutant which coincides, given any vector, it coincides on that. Okay. So that is what the statement is. Pi of x xi tilde is equal to this. So this thing implies x acting on xi equal to A naught acting on xi for all I. Okay. But since xi is a basis, it's a basis x equal to A naught. That's what we wanted to do. Okay. This whole thing implies A is equal to A double commutant. Okay. Read out.
It's kind of taking a commuter in each of the components.
Where?
So like pi of A commuter, when pi of
Correct,
A is
correct,
one
correct.
tensor A.
If you take A tensor B, then the commutant is A commutant tensor B commutant. Correct. You're absolutely correct. Because it's one. That's okay. Good. It's spelled on precisely like this. I'm very clumsy all that. Yeah. I mean, that is not easy to prove. One has to sit and but this kind of thing is easy to prove. In general, for A tensor B, to prove it, even for Hilbert space, it's not that easy. Okay. So we have proved A equal to A double commutant. Okay. If you have any doubt, we will discuss in the next class. Okay. So corollary to this, that is the question thing he asked. You asked. He asked, I think. You asked that question, spectral projections in the algebra. So, yeah. So it will follow.
So
Scroll up. So except him, everybody is in BSc, right? You are in BSc? All of you are in BSc. You haven't done measure theory yet. Where? In Karandikur course. Okay. That's good. That's enough. You haven't. If you know what is a measure, just definition, that's fine. You don't need all that. I mean, for the time being, you don't need. But you have to be very familiar with the sigma algebra and the language of measure theory. Okay. Maybe not the proof, which you can learn it sometime. If you are doing mathematics, certainly you have to learn measure theory at some point. Okay. So you can't avoid it. So the corollary is the following. X is in A. Okay. A self-adjoint. Self-adjoint element. That means X is equal to summation lambda I EI. Where EI is spectral projections. Okay. Lambda 1 up to lambda K are eigenvalues.
So you mean X equal to X star?
X equal to X star. Yeah. Self-adjoint. X equal to X star. Self-adjoint. By spectral theorem, X looks like summation lambda I EI. Where EA is a lambda 1 up to lambda K are eigenvalues and E1 up to EK are spectral projections. Okay. Spectral projection.
So is this how you define spectral projections?
Huh?
Like,
Yeah, this is what they are, spectral projections. They are called spectral projections. Okay. All the eigenspaces. Projection onto the eigenspaces is spectral projections. Okay. So what does it? So suppose A commutes with X. So suppose A in MNC. I mean, let's take the algebra generated. I don't even need A. I just take the algebra generated. I just take MNC. I just take it in MNC. Okay. Suppose A commutes with X. AX equal to XE. Just AX equal to XA. That's what I'm saying. I mean, I'm not talking about the algebra now. I'm just taking AX equal to XA. Okay. What does it mean? That is X commutes with A commutes with X. Okay. X is self-adjoint, so it commutes with the star also. The star is same. So what does it mean? It commutes with all those things. That means see, with respect to the spectral projection is something look like this. X looks like this.
what is A?
A is something in MNC. It commutes with this. I'm just trying to compute the commutant of the algebra generated by X. Okay. So X is some, how does X looks like? Lambda 1 times E1. Okay. Which is just, I mean, it's not a single entry. I mean, it's just the, it is just the projection onto that. Okay. Lambda 2 E2, it looks like this. Lambda K EK. I mean, it's actually lambda 1 repeated many times there. I mean, even as a projection like that, it will look like this. Okay. Now, AX equal to XA means A should look like some X1. Okay. Some operator X1, because it's, I mean, any X1 will commute with this, where X1 is an operator on the subspace corresponding to E1. E1 gives eigenspace, no? X1 is an operator. So it's something like this, X1, X2 up to Xk, 0 everywhere. Where Xi is an operator, if you wish, if you don't mind, I wrote B of range of Ek, range of the eigenspace, Xi, Ei. Ei is a projection, range of Ei is the eigenspace, and B of an operator, just a matrix on that subspace, that is Xi. So that if you put it, that is what is A should look like, right? If you commute with that, you just do the computation. I mean, what it means by commuting. If you have a scalar, lambda 1 up to lambda n, something commutes, it has to be scalar again, right? If you have a diagonal matrix, something commutes with all the diagonal matrix, that has to be a diagonal matrix again. So if it commutes with that the lambda one, yeah, it has to commute with the lambda times E, that projection. So it has to, I mean, that lambda one is just a single lambda one, okay? So it has to look like this, okay? Okay. So now this implies EI commutes with X, EI X equal to XEI for all I. When I take an operator A, if it commutes with X, it will look like this. From that, I conclude that EI actually commutes with this. That is clear, no? Because EI is a projection which will only act on that entry, right? So it will commute with that. So these things implies that EI is in the commutant of the commutant of X.
So does it follow from like each xi being commuting with each EI?
Each xi will not commute with xi is just an operator. Xi is an operator on the space corresponding to EA. There is no commuting with that. It will commute with every operator on EA. Sorry. It commutes with the scalar, so it is some operator on EA. It doesn't commute with that. See, wait. See, this is how X will look like. Lambda one. It's just lambda. This is an eigenspace. This is an eigenspace. It's like you just arrange the eigenspace like this. So x-axis or x-axis lambda scalar lambda one here, which is eigenspace. X-axis scalar here, scalar here, scalar. If something commutes with that, you do the computation. I'm not doing the computation. I'm leaving the exercise. That just means it is some operator here. And it has to be zero. It shouldn't take something from here. So it should be zero here. It will not take something from here to here. And then some operator here, some operator. That is how A will look like. Okay. Or maybe I should put A or something. Maybe not XI. Let me put A. A1 up to A. Okay. That's better. Okay. So that is how A should look like. Okay. X is commuting. Where AI is. Okay. Now this implies that EI commutes with X. EI commutes with A. Sorry. Oh my God. EA will certainly commute. EA commutes with A. Okay, that's what I want to say. I'm sorry. I got confused with X and A. EI commutes with A. That's what I'm saying. So what it says is if A commutes with X, we started with X, no? A commutes with X. Then each eigens projections also commute with that A. So this just implies EIs are in, you take the algebra, star algebra generate, I mean, there's no star algebra, it's self-adjoint. So algebra generated by, we started with X, no? X, algebra generated by X. If you take the algebra generated by X, okay, EIs are in the double commutant of that. That's what this says. But this is equal to algebra generated by X, which we approved just now. Double commutant theorem, we proved. Okay. So this just says that if X is a self-adjoint operator, X is a self-adjoint operator, its spectral projections are in the algebra generated by that X. That's what this says. So in particular, the answer to that question, in particular, if X is in A, algebra generated is the smallest algebra generated by A. That will be contained in any bigger algebra. So if X is in A, then this implies all spectral projections are in A. X is in A and self-adjoint. X equal to X star. Then spectral projections of X are in A. Okay. Are contained in A or what? Okay. So if some X is in A, then the spectral projections are also contained in that. So we can talk about the probability and all that. Okay. So when we have a state on A, then we want to talk about that gives a probability distribution on the eigenvalues, set of eigenvalues that we can talk about. Just it is just the state acting on that spectral projection, which is in A. So you can talk about that. Okay. So this is justification for that. So if you have any self-adjoint operators, and if you have a state on the algebra, and if you have any self-adjoint operator, then you can take the eigenvalue, set of eigenvalues of that self-adjoint operators that give a probability distribution of finite probability distribution. Okay. To do something similar to that for infinite dimension, we need spectral theorem for a self-adjoint. If you this I said last time, if you take any self-adjoint operator X, then you have eigenvalues lambda 1 up to lambda k. Okay. Then on the lambda 1 up to lambda k, which is a finite probability, a finite sample space, on that you get a probability distribution where probability of that lambda k, x equal to lambda k or whatever. So if x equal to x is a self-adjoint operator and is in A. Okay. Then if lambda 1 up to lambda n, lambda 1 up to lambda k eigenvalues. Values and phi is a state. Okay. Then you get a probability distribution. We get a probability distribution. Probability distribution on this sample space lambda 1 up to lambda k, given by probability of x equal to lambda I is equal to phi of ei, where ei is the eigen projection. Projection corresponding to lambda I. Okay. Okay, that's how we come to. And usually this phi is given by a rho, I mean another positive operator or something, then you can come. So this is a bit. For that, we need to justify that. That's the right question. For that, we need to justify that EAs are in the algebra. If it is everything is in MNC, we don't have to do it. But when we restrict to an algebra, we need to do that. So this is the justification. Okay. So we'll stop.